S. Okay. Hi. So today I will finish this AVL. So today I'm going to give the AVL tree balancing. I'll finish where we stopped on uh Friday, last Friday. Then another topic, a very short one, will be about the Huffman Coding tree. It's just show you just one of the application by using the binary tree to solve some problem. And I just update this particular slide about the AVL tree. There are some mistake which I think last Friday I have made a mistake here. Originally this one last Friday I said is the n. It's not correct. It's supposed to be n log n, because every time you let's say if this particular tree, where's my pen? Yeah, if this particular tree is the something like a balanced tree, that means you something like a complete or full binary tree. Every time you insert a node, you expect that first time you insert at the top at the root, then it's just one comparison. If it's the second time you insert it, you need to compare this one times. Then the third time you insert it, probably will be at the right side. Then you will be maybe the right side, maybe left side, doesn't matter. But you need to have at least 1 to 2 comparison. So eventually you build out this whole tree. The total number, of course, you insert n nodes. Every node, on average, you need to take log n to insert it. Because you need to travel in the tree, you will take log n times. So you insert n times, so it should be n log n. And for this particular, to construct this most balanced binary search tree, you need to go through the should be before that. I need to do the in order traversal. So I did the in order traversal, so I need to have an additional array to store the in order traversal result. So this particular in order traversal result will cost me additional big theta n in the space complexity. So this just want to show you that, well, get the most balanced binary search tree, you can have a better binary search later, but the cost is not cheap. The time complexity is n log n, and the space complexity, you need additional array to store the data, which is not, if your n is large, this is quite expensive algorithm to build the most balanced binary search tree. So people start thinking that whether they can have some algorithm, they don't really need the most balanced, as long as the tree is quite balanced. It's quite balanced, and you won't end out to have a binary tree which look like a linked list. That's when you have one subtree with a very long list, all are left child or all are right child all the times. So we try not to have this. But if you just simply, every time you just simply insert a node one by one in arbitrary order, there's a very high chance that you insert a node, and now it may become a long linked list. And like for example, I think in the last lecture I have shown you one of the example is like, if you insert the nodes in ascending or descending order, like 9, 8, 6, 5, 3, in descending order or ascending order, you will find that if you insert the nodes in this order, your binary search tree will be, it's a binary search tree, but actually the structure is like a linked list. So people start thinking, yeah, it's very expensive to build the most balanced binary search tree, and how do we improve it? So they come up something like, I just need to, every time I insert a node, I'm trying to locally balance it. That's so-called the AVL tree, which the height of the left and the right subtree of every node different by at most 1. This is where we stop on last Friday lecture. So I have shown you that to locally balance the the tree, yeah, you need to know what is the balance factor. So balance factor is trying to measure the height of the left subtree and the height of the right subtree, the difference between the left and the right. If the left subtree and the right subtree different more than 1, yeah, that means one of the subtree is too high, more than 1, then you need to do the balancing. So very soon you will find that for nodes insertion, there are 3 cases. The first 2 cases, there's no tree balancing issue, because when you insert, like in this example, if you insert a node like 25, which is along the path, all the nodes are balanced. Yeah, that means the balance factor are 0 along this path. This one is 0, this one is 0, this one is 0, this one is 0. After you insert a new node here, the overall along this path is still balanced, because they all are 0. So you add additional 1 node. Yes, one side will be higher a little bit than the other one. But like this one, 23, node 23, after you insert 25, node 23, the balance factor will be decreased to -1, because left side is 0, right side is 1. Left side is -1, sorry. Left side is -1, right side is 0. So the balance factor at node 23 is -1. It's still balanced. It still fulfill the AVL tree balance binary search tree condition, the definition. So it's still considered this particular tree still a balanced binary search tree. 31, these nodes, left side 2 nodes, the left side, the height of the left subtree is 1, the right subtree is 0, so 1 minus 0 you get 1, so still balanced. Then 14, nodes 14, you have 1, here got 2, so 1 minus 2, you still get -1, still balanced. Then 70 is 1, 2, 3, so here is 3, here is 2, 3 minus 2, still 1, so it's at most 1. So the height of the left and the right subtree of every node still different by at most 1. So this is considered the balanced AVL tree or balanced binary search tree. So there's no balancing issue after you insert 25. Expected, because as I said, these all are balanced nodes. So well balanced, perfect one, 0, 0, 0. All the balance factor is 0. You adding additional 1 nodes, it won't affect the balance factor. It will affect the balance factor, but the difference still at most 1. So not possible more than that. You just add 1 nodes only. Same thing for nodes 80. Nodes 80, if you insert it, you probably will insert to here, which is trying to, along this path, 93 is, the left side is 93, the left side of 93, the nodes is this part, originally this part the height is 0. This part the height is 1. So 0 minus 1, which is negative 1. After you insert a node 80, so you are insert at the subtree which is shorter than the other subtree. So in that case, you will become, this side will become, after you insert 80, will become 1. So 1 minus 1, so you get 0. So overall, along this path, because every time you insert a new node, you only affect the balance factor of nodes along this insertion path. That means you only will affect 70, 93, and 73. These 3 nodes. After you insert 80. In that case, the rest you don't need to care. You just need to mesh to re-evaluate the balance factor along these 3 nodes. And you'll find that all these 3 nodes are the balance factor still different. Yeah, the balance factor still is negative 1, 0, or 1. In this case, this whole binary search tree is still considered as an AVL tree or balanced binary search tree. So there's no balancing issue. Only the case tree I have mentioned. Yeah, you expect that only these 4 scenario. You are trying to insert a node at the left child of the left subtree. You are trying to insert a node somewhere here, and you are trying to insert a node at the right child of the right subtree, and this particular subtree is higher than the other subtree. That means the left subtree is higher than its right subtree. Or this particular case, the right subtree is originally, before you insert, is already higher than its left subtree. In this case, you add 1 more node here, or you add 1 more node here. These nodes will become unbalanced. We need to balance these particular nodes. So similarly to the left child right subtree and right child left subtree, you are trying to, in short, case 3 is you're trying to insert a node at the subtree where this subtree is higher than the other counter subtree. So if you insert the nodes at the left subtree, which means this left subtree is higher than its right subtree. It's already higher. After you insert, it will even higher than that. So you will become, your balance factor at these nodes will be more than 1 or less than negative 1. So last Friday, I have shown you, if you are trying to insert, for example, 95, you can see that if you're trying to insert 95, you will move along this path. 95 is greater than 93. 95 is lesser than 99. 95 is lesser than 97. So you will insert as the left subtree of 99 of its left child, as a left child. So it's so-called, here I name it LL case, left subtree. Yeah, the left child of the left subtree. The left child, yeah, of the left subtree. The left child of the left subtree. So in this case, you expect that at nodes 99, this nodes 99, you can see that from here, nodes 99, the left side after insertion, the left side, the height is 1. The right side, nothing. So it's negative 1. So 1 minus negative 1, you expect that 99 will become, the balance factor is 2. So that means you need to do the 3 balancing. By doing this, that means in short, you need to do the right rotation about nodes 99 to rebalance the tree at that particular node. And what is the idea? What does it mean to right rotation? You are trying to move some nodes at the left to the right, so that you can balance the balance factor at nodes 99. So that is the path. By doing this, okay, I think the order. Okay, I need to first update after you do the insertion. After you do the insertion successfully, you start return back to node 97. First, you need to update the height of node 97, which is from originally nothing, which is the height is at 97 is originally is you only one node, so the height is 0. So now you add one more 95 at the left child. So this the height of 97 here, this sub 3, the height is 1. After update, the height will become from 0 become 1. Then you update the balance factor. The left side is 0. The right side is -1. 0 minus -1. 0 minus -1. 0 minus -1. So the balance factor at 97 is 1. So it's 1. It's updated. So updated. Then I trying after this one updated 1. So it still fulfill the balance binary search tree, AVL tree. I still fulfill, no problem. The problem is at 99. When I go back to 99, I do the same thing again. I update my height at nodes 99. Now the height will become 2. The height of 99 will become 2. And then I update the balance factor. Balance factor, because 97, the height at the left sub 3 is 1. Right sub 3 is -1. So which is 2. So in this case, the balance factor at 99 at this moment is 2. So not okay. So I need to do the balancing, imbalance at node 99. I need to do the tree balancing at node 99. In that case, I need to do the rotation. So by doing this rotation, I need to move this up and move 99 down. And bring whatever here. Just nice that this one is null pointer, so you don't have to do anything. Otherwise, the nodes 97 right child, which is now at this moment, will be the nodes 99 left child. In this case, if there is something here, you will put it as a left child of 99 first. And then let the nodes 99 be the right child of nodes 97. So you will shift now. You will bring your 99 now and then move 97 up. And 97 be the 93 right child. Replace the 99. So the rotation, is it the biggest nodes on the left side? The biggest nodes on the left side will go to... No, not the bigger nodes. The whole sub-tree. If here there's something, if there's one sub-tree here, you will bring the whole sub-tree to, from the, the right child be the left child. So you will bring the right sub-tree of 97, the whole sub-tree, to be the 99 left child, left sub-tree. Okay. So after that, you will get this. So if just now here, because in this case, the tree structure, so I don't have anything at the right child of 97. Otherwise, you expect that there's something here. if 99 have a right child, the right child will still remain there. If there's something here, it still remain there. After you do the right rotation about nodes 99. Once you have done this, you can notice that the nodes 99, the balance factor is 0. The nodes 97, the balance factor is also 0. Then subsequent, this one will still remain -1. This one will still remain as 0. 1, 2, 1, 2. Yes. So that means the whole binary search tree, you just need to do one rotation. You will balance. So this is the first case. Okay, we try another way. So this one, yeah, this is the this one. I think this week I also asked you to try to implement the right rotation or left rotation and see how it works. You can try it out. Okay, so the left subtree will always take its place if do the right rotation. So the left. So after rotation, if 99 left subtree should be originally should be 97 right subtree. That means if you have something, let's say you do the rotation, there are something here. While you do the rotation, there are something here. After rotation, this particular subtree, the right subtree of 97, will become the left subtree of 99. Okay. We can think the other way. Now we think about the other case, which you need to do the left rotation, symmetric. Yeah. The second case is the RR case. That means you're trying to insert a node at its right subtree of the right child. The right child of the right subtree. The right child of the right subtree. So in this example, I'm trying to insert 12. Insert 12. You will insert 12, 12 is smaller than 70. 12 is smaller than 14. You will travel, you will search the place. 12 is greater than 7. So you will go to the right side. So this is the right subtree of 7. 12 is greater than 10. So you're going to insert your 12 here. So in this case, you can see that these nodes will be unbalanced. Node 7. Because the left side is nothing. Right side, originally there's a node 10 over there. Then you further add another one more node at its right, as a right child of node 10. So you will end up that node 7 will, node 10 is still bad, is still okay. At least after you update the balance factor. Okay. After you add the balance factor, after you add these nodes, the balance, I forgot to update the thing. After I add this one, okay, maybe I should do here. After I add these nodes, the balance factor of node 10 will be -1, right? Then it's okay. It's still in the, the difference is not more than 1, still okay. 7 will become, right side is negative. Yeah, this side nothing, so -1. Then this side is 1. So -1 minus 1 will become -2. In this case, you need to rotate left. And how to rotate left? You will see same thing. Yeah. Why do we need 97 right child be? If if 97 right child not to be the Nooks 99 right child, then how to let 99 be the right child of 97? So same thing. Now let's set here after you insert 12, you notice that it's the same things as this left rotation. You definitely want to move something to the left side of Nook 7. So what you need to do is do the left rotation. By doing left rotation, what you need to do is also same idea. You will take all the nodes at the left subtree of node 10, the left child. Node 10 left child be the node 7 right child. So node 7 is here. You must bring all those things at the node 10 left child, left subtree to be the right. Then your node 10 left side now is free. Then you can let your node 10 left child, node 10 left child, yeah, will be node 7. Yeah, that is the reason why you need to move all these the left subtree of node 10 to be the node 7 right subtree. By doing this, so that your node 10 the left side is free, so you can connect to the node 7. Then here still remain as 12. Yeah. So this is the left rotation. After you do the left rotation, you can see that the balance factor in every node will become, yeah, either 0, 1, or -1. So the tree is a balanced binary search tree, or AVL tree. Yeah, this is two, and then another two cases. You can insert the nodes at the left subtree, the left nodes of the left subtree, or the this one is the right nodes of the right subtree. That's when there are another two more cases. The next one is the LR. That's when you're trying to insert like 98 to the right nodes of the left subtree. The right nodes of the left subtree. The right nodes of the left subtree. In this case, you need to do two rotation. You need to do the left rotation. You need to do the, it's obviously 99 is still unbalanced. You insert additional nodes to the higher sides, to the higher subtree. Definitely nodes 99 will become unbalanced. So in that case, you need to do the left rotation. After you done the left rotation, then you will be same as what you see earlier. Then you just do the right rotation. Then everything will be balanced again. Got it? So this is the LR case, which you're trying to insert a new node to the right nodes of the left subtree. Right nodes of the left subtree. And the left subtree is higher than the right subtree. Originally, the left subtree is already higher than the right subtree. You further add one more node, you need to do the left rotation and then right rotation. If you don't do this, probably maybe someone will trying to think that why not just simply do the right rotation. If you only do the right rotation, in this case, you will find that you will bring the 97 up, then 99 will be here. 98, because whatever here, 98, you will pass to 99 as is left child. If you only do for this particular case, if you only do the right rotation about nooks 99, you just simply do the right rotation, this will be the result. In that case, you will move 2 nooks to the right subtree, then left side have no nooks, then the tree will still unbalanced. So the correct way is, first you need to do the left rotation about 97 to make them all at the left side. Then you do the right rotation. Symmetric, another example, the last case, which is the RL case. You're trying to insert the new nodes into the left subtree. The left subtree is higher than the right subtree, and of the right child as a right child there. In that case, in this example, I'm trying to insert 8. So 8 will be this 10, node 10 is the right subtree of node 7. You insert it as the left child. In this case, you also need to do 2 rotation, same as the previous case. First you do the right rotation about node 10. This will be the result. And then you do the left rotation. Then the tree will become a AVL tree, or balanced binary search tree. So this is AVL tree is trying to do this balancing by do the rotation about at the unbalanced nodes. Okay. Yeah, in fact, there are a lot of other self-balancing binary search tree. So not only this one. So again, I'm not trying to, I cover this AVL tree is not ask you to go and memorize the algorithm. Probably this algorithm, as I mentioned, is already in 1962, is it? Yeah. So by two Russian is for many years ago. In fact, today you find that a lot of library already have this algorithm to do this tree balancing. The idea you need to know is trying to understand how they analyze the problem and how they categorize to find out there's a big problem, you need to do the tree balancing. From this big problem, they will find there are 4 cases. And among these 4 cases, in the end, they find that there are only 2. You just need to find out how to do the right rotation and left rotation. And you can solve that 4 unbalancing issue. And you can do the balancing. Yeah, you can balance the tree. After that, then you get the balanced binary search tree. In fact, there are a lot of people have proposed a lot of different algorithm to balance the search tree. Yeah, or different search tree structure. Yeah, here we not cover all this. If you're interested, you can go and search. Yeah, red black tree is another one. Maybe you will cover B tree and red black tree. Yeah, it may cover in the higher level. Yeah, there are a lot of people trying to keep thinking, because one thing is you can see that why they need to do that is the earlier one, the most balanced binary search tree, the cost is too high. Yeah, every time you need to do this, you insert a new nodes, you need to have additional an array, and then you need to reinsert the nodes is n log n. And every time you insert a new nodes, you need to do so. So will be cost is too high. So people start thinking, like by this thing, you can see that every time I insert a node, I just locally rotate one node. So I insert a nodes, the travel time is log n. After I insert the nodes, you will find that these 4 cases, I just need to rotate once. So that means it's a constant time. In all the 4 cases, I just need to rotate 1 node. You can go and observe, you only need to rotate 1 node. If it's an unbalanced node, only 1 node only. After you rotate at about that particular node, 1 times or 2 times, the tree will be balanced. So that means this process is a constant time. Because every time you just need to do the rotation once or 2, up to 2 times. So it's a constant time. So overall, the nodes insertion with tree balancing, the time complexity should be big theta log n. How do we know when to use the LR and RL? You will check the balance factor. Every time after you insert the nodes, you return, you will update the height and update the balance factor. Once you found that the particular node's balance factor is not 0, -1 or 1, you know that this particular nodes need to do the tree balancing. And you know where you come from. Where you return is from the left side or the right side. Which means you can see that how to do. Yeah, when you can see, for example, this case. Maybe use this as an example. I'm trying to insert nodes 10. And I'm trying to insert nodes 8. So first, the algorithm will trying to do the traversal. 8 ma. 8 is smaller than 70. 8 is smaller than 14. 8 is greater than 7. 8 is less than 10. So you will insert the nodes here. After you insert the nodes, you will update the height, update the balance factor of 8. Of course, this is the new nodes, definitely no problem. You return back to nodes 10. After you return to the nodes 10, you update the balance factor. So this one, you update the height and the balance factor. The balance factor will become 1. Because the left side is higher already. So this one, 1, no problem. So you will go higher. So when you go to node 7, is negative. From -1 become -2. Then you find that node 7 is unbalanced. Then there's a problem. So you need to do the tree balancing. It can be, okay, if you only know the balance factor is -2, it can be something in this way. It also can be just now insert 12. If it's 12 also possible. If it's a 12 also can be -2. So you need to check the right child. So you check the right child's balance factor. You will know that it's at the left side or the right side. Is the left subtree higher or right subtree higher? Then you will know that you are the RL case or RR case. I think there's no problem between LR case and RL case. You only have the problem is like when you find that the nodes is unbalanced, you do not know whether it's a RL case or RR case. You need to check the childs. You only check the childs, you know. You check the child's balance factor, you will know. Is the left side higher or right side higher? Then you will do because the purpose you do this rotation is trying to let the left side. First, I do the right rotation about node 10. Is trying to let the right sides higher first. Then you do the left rotation. Because I need to make sure the node 10 left side is higher. After then the second step, after that, this one you expect that the right, after you do the right rotation, the right side will be higher. And then you go to the node 7, you do the left rotation, then they will balance. Okay. Yeah. So that is the thing. You can see from here, you will bring everything to the left side. So now at this particular subtree, the left side will be higher than the right side. So after that, you do one more left rotation. Then this particular part will be balanced. Okay. Yeah. So there are a lot of you can go and if you interest, you can go and study these few tree and more. Actually, there are a lot more. Yeah, red black tree and B tree normally will cover in higher level. Yeah, so just let you know. Yeah, there are a lot. Or generally, all these three the time complexity they were trying to maintain at about log n. So that every time you insert a node, the cost is not that high compared to the earlier you see the most balanced binary search tree, which is n log n. How do we know we need to do RR or RR? No, should be RR or RL, is it? About 7. This is RL case. Yeah. In that one, as I mentioned just now, when you at the node 7, in both cases, at the node 7 will be -2. If we go back to LR, yeah, this one also -2. Probably I need to switch between these two cases. Okay, you can see this is in the RR case, you can see that node 7 is -2. But node 10, the balance factor, after you do this thing, I think I should change it to, it will be, should be -1, -1, 0. So should be -1. I think this one should be -1 after insertion. This one should be -1, right? But still okay, -1. Yeah, it will be from 0 to -1 after insertion. Then this is RR. Then the last one, this one will be after insertion, it will become 1. It will become 1 after you insert the nodes at here. So you just determine whether it's 1 or -1. So if it's 1, if it's -1, the right child's, you find that this is -2, right? Then you just check the balance factor of its right child. If the right child's balance factor of the right child is -1, you know that this is a RR case. This is a RR case. You just need to do the left rotation. But if you find that it is a RL case, then you will find that after you insert the new nodes, this one will be -2, and then node 10 will become 1. That means the right side is higher than the left side. If your balance factor is 1, means that the left side is higher. So you need to do the right rotation to bring some nodes from the right, from the left to the right. You do the right rotation. You will bring some nodes from the left to the right. And then you do the left rotation, then you will be balanced. Yeah, I as I said, you don't have to go and try to. You can go and find. I think you can quite easy to find out the full implementation of all these 4 cases of the AVL tree. Yeah, but I'm not asking you. That's why I didn't ask you to implement the whole thing. At least, but what you need to know, I think just like what I ask you to do in the lab, I trying to let you to know how to implement the right rotation and left rotation. Yeah, this thing you should know how to do it. You need to know how to do the rotation or change the tree structure somehow. Yeah, I think this is something useful. But to memorize this AVL tree is not that. You just need to know the idea behind there are few cases there. Yeah, the concept you need to know. You don't have to really implement everything by your own and trying to memorize them. You need to be able to implement them in, I think, maybe in the future, but not really need to memorize how to implement them for the test. Yeah, you need to be capable to implement. So that's why I only ask you to do the right rotation, left rotation. You need to know how to calculate the balance factor, how to calculate the height, how to calculate the balance factor. Yeah, I think this element is maybe useful to solve other problem in the future. But memorize the whole algorithm, how implementation, yeah, you may find that no point to do so. Yeah. So need to know what you need to learn. Don't spend the wrong times to learn the wrong things. Okay, so yeah, because there are so many trees. If you go and check the red black tree B3, you'll find that their algorithm is more complicated than this particular one. Then really need to memorize all of them. Even you memorize it today, probably another few weeks later, you also cannot remember. So become pointless. But trying to learn how actually do the left rotation, right rotation, balance factor, how to calculate the height. Yeah, it may be useful to solve other problem. Maybe not doing the left rotation, right rotation. Yeah, just like you want to change the tree structure. Sometimes you need to do something. Yeah, on the notes. Yeah, it may be the technique, the trick behind. You can learn and use it, apply it. So this is something you need to know. Yeah. You will find that this is not the only balanced search tree. There are a lot more. And this one is already, I think it's more than 50 years ago algorithm. And a lot of this kind of algorithm is developed in the during the World War II or Cold War. Yeah. Due to US and Russia, then they will develop a lot of this kind of algorithm during that period. So yeah, in the binary search tree, we have give you the definition. So node's value is greater than all value in its left subtree. Then node's value must be less than all value in its right subtree. And both subtree, yeah, of the nodes are also the binary search tree. That is the definition. And we also show you how to do, just simply do the nodes insertion and nodes removal. This, which is also this week, the lab question. Of course, you can insert nodes, remove nodes. You need to know the height of the tree. And then soon you will realize that some tree, the structure is not good. Then you need to do the tree balancing. Here we only introduce you one of the well-known tree balancing algorithm, which is known as the AVL tree. So you find that AVL tree, there are three cases. Two of them, you don't need to do any tree balancing because they insert the nodes into the subtree, which is same as the right subtree, or they are the shorter one. If you insert a node at the subtree which is higher than the other subtree, before you insert is already higher. So you further add one more node, it definitely become even higher. So in that case, you need to do the tree balancing. And you will find that do the tree balancing, you just need to do on one node. Yeah. It can be do the left rotation, right rotation, or right rotation, left rotation, or just simply do the left rotation. Overall, yeah, this is the, yeah, if you have the nodes, let's say I have the nodes alpha, beta, and this is gamma, I guess. Yeah, this is the subtree. All of them, let's say you have the subtree. X and Y is just single nodes. Then if you're trying to do the right rotation, that's when you will bring the Y come down. Then this beta subtree will pass to be the Y left subtree. And then X will become the parent nodes of Y. Yeah, so Y will become the right child of X after the right rotation. Then if you have this particular tree and you want to do the left rotation about X, then you will bring everything back to here, like what you see. So Y will back to the parent, become the parent of X. X will be its left child. Then this beta subtree will become from the Y, which is originally is the Y left child, then now become the X right child. So this is the relationship between the left rotation about X and right rotation about Y. Okay. Okay, last I going to give you example, another things. Okay, Huffman Coding tree. This is just an example to show, again, I'm not asking you to implement this particular algorithm, just show you that, how this binary tree can be applied into some real world problem. So Huffman Coding is a greedy algorithm. Yeah, the coding tree is built out based on the frequency of occurrence of each character. And the code, is a variable length code. For example, what you have learned, you usually use the ASCII code. ASCII code is a fixed length code. That means you only use the 7-bit to represent all the character. You can represent up to 128 character. Yeah, by using 7-bit, 2 power to 7. Yeah, so you can represent all these character. And then variable length code, the idea of the Huffman coding is like, you will find that, for example, A to Z, if you use a fixed length, that means all are using the same number of bit to represent it. In that case, for example, if today I want to develop a system only A to Z only, I just need A to Z, which is 26 character. 26 character, how many bit do I need if it's using the fixed length? How many bit do I need? If I just need to represent A to Z, 26 character. How many bit do I need? (26 character, 5 bit. Yeah, more than enough. Because 5 bit, 2 power to 5 is 32. 32. I can represent up to 32 character. No. You have 26 character. A to Z. Yeah, you want to find a way to represent them. You just need 5 bit. Because 5 bit, there are 32 combination. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on and so forth. So 32 combination. So it can be well represent A to Z. So in that case, 5 bit is good enough. But you will find that by doing this, maybe not very efficient. Because sometimes maybe A, E, I, O, U, maybe you use more frequently. Some alphabet like Q, like Z, maybe, I don't know, maybe X. Yeah, is some alphabet you seldom use it or use lesser. The frequency of occurrence is less frequent than A. or E, I, O, U, this few character. So in that case, maybe this is not, yeah, so the Huffman coding is trying to think how to use fewer bit to represent the higher, more frequently used character, and use more, and maybe you can sacrifice and then use more bit to represent those less frequently used character. In that case, you will find that later I will show you, you will find that overall the total number of bit to represent the data will be lesser. So you can save more space, storage. Yeah. So this is a kind of also can consider is a data compression. Yeah. And lossless. That means I won't lose any accuracy. It still can recover exact data by this data compression. Another thing they want to do on this Huffman coding is like they want to make the, yeah, there's the prefix code. That means no code word is also a prefix of other code word. So that later I will show you, you will find that by doing this, yeah, you can easily decode it. For example, this one 0, 0, 1, 1, 1, 0, 1, 1, 1, this representation is not a prefix free. The first one is 0, 1, 0, 1, 1, 0, 1, 1, 1. The reason is because the first two, 0 and 0, 1. If I only give you, if you have a data 0, 1, 0, 1, 0, 1, you, for example, that's when if you have a code, you will not be able to decode it uniquely. If that is the case, that means, yeah, it's not a prefix free code. Yeah, so this particular things is developed by this person, David Huffman, in 1952. So it's already 70 years ago stuff. But we still using it in today. Yeah, when we have some data, we found that some data we use more frequently, some data we use less frequently. We want to find a way to code it to save, to improve our search time, to reduce our storage. Yeah, when all these problem you encounter, yeah, you may do this kind of coding. Of course, there are a lot more other coding method. Here I just introduced this one, which is related to binary search tree. So give you an why do we need to do this? First, just like I mentioned, let's say you have 100,000 character to store. If you use the fixed length code, that means in this case, for example, I only have A, B, C, D, E, F, 6 character. Then let's say I use the 3 bit to store. Yeah, if that is the case, you need to use 300,000 bit to store. But if I using the variable length code, then which I just, yeah, then A I use 0. Yeah, then B, because A, the frequency is 45% of times, so I just use 0 to represent. B, 13, 12, 16, all this, maybe I use 3 bit to represent. Then E and F, let's say is less frequently used, so I use 4 bit to represent. If you go and do the calculation, 0.5, 0.45, you use 1 bit, 45% times you use 1 bit, 13% you use 3 bit, 12% you use 3 bit, 60% times you use 3 bit, 9% and 5% you use 4 bit. Overall is on average is 2.24 times 100,000 character. You just need 224 bit to store this 100,000 character. And you save about 25% space. Yeah. So this is one advantage using variable length code. Another things, yeah, this particular Huffman coding is the prefix code, or they call prefix free code, or some people call free code. In short, if I give you this data, you definitely can decode it uniquely. So you can see that by this one, you can easily find out that if you read from here to here, you read from here to here. When you read 0, okay, then definitely this is A. Yeah, because here only 1, 0. Then 1, 1, 1, 1, 1, 1, which is D. Yeah, after you read 3 bit, you know that this is D. 1, 1, 0, 1, 1, 1, 0, 1. After you reach this point, you know that there's a E. Then 1, 0, 1, 1. And 1, 0, 1. Sorry, 1, 0, 1. B. Then the last one is 1, 1, 0, 1. Yeah, you will find that you are not able, to have any ambiguous code in the Huffman coding. That's the only way you can uniquely recover the actual, you can decode it. So this one is very useful. Normally you need to do the transmit the message. Yeah, you want to use the lesser bit to transmit. And you also need to ensure that the receiver sides can decode it uniquely. Yeah, so there's no any ambiguous. Yeah, maybe it's A, maybe it's B. Of course, we don't want to have this kind of communication. So in that case, this one definitely, Huffman coding can be used. You not only can set the space, you also ensure that you decode, you won't get the ambiguous code. So that is why we need to use the Huffman coding. And the next is how to do it. How to get this particular code. How to get this code word. How do you know which one is 1 bit? Which one, how many bit do you need for each character? And what are they? So actually, if you look at this particular code, you can find that you can build up a binary tree. If you move to the left, you're trying to, if it's 0, that means you start from the root, then you're trying to travel to the left if it's 0. If it's 1, 0, 1, that means it's 1, 0, 1. 1, 0, 1, 0, 1. Yeah. You move to the right if it's 1. 1, 0, 0, 1, 0, 0, C. Yeah, which is 1, 0, 0. They always have the unique path. D is 1, 1, 1. 1, 1, 1. So it's like always every bit is either you move to the left or move to the right in this binary tree. So therefore why they are prefix free. Why they are prefix free code? Because each path, they only have one. Eventually they only reach one character. So their prefix is definitely unique. You will find that actually only one, only A is start with 0. The rest are start from 1. All these things start from 1. From the tree can explain why. There's a proper mathematics proof lah. Here I'm not interested to go through that particular proof. Intuitive, you look at the tree, you can understand why it is so. Then you move to the left, there are only B and C, but only B is 101 and only C is 100. So it will be very unique. After you receive 3 characters, you can determine whether it's B or C. If it's not B, not C, definitely it's 1 something. So this is the Huffman code. But how to build this particular tree? Because today if I only have A, B, C, D, E, F. You have a set of data. And from the data, you can do some statistic to find out that, maybe A, you will use this particular data 45% times you use A. You got 13% times you use the B. And then 12% on C. And then 16% you use the data D. And so on and so forth. How do you come out the code word? So how to do this, how to construct this particular tree and come out all the code. This is the algorithm. And how this algorithm works. First, you create the nodes. You create each data, you create the nodes A, B, C, D, E, F. is the data is the correct. Here I use I use a character. In fact, not only character, it can be anything you want to use the X bit to represent. So let's say I want to use to store this 6 character A B C D E F. So in this case, I also know their frequency. Yeah, 45%, 13%, 12%, 16%, 9%, 5%. Then I create the nodes for each of them. Then I also I start build the tree. So I create a node Z. Okay. Then among A, B, C, D, E, F, I look for the smallest frequency one, which is F in this case. And then the second smallest one, which is E. Then I sum it up. 0.09% plus 5%, which is 14%. I sum it up. Then I construct the tree. I construct a subtree. So I construct a subtree here. Then I add this Z. Let's say this is called Z. This new subtree, this node is called Z. I add this back to the list and do the repeat this process again. Yeah. So you carry on. Okay, quickly go through. Then you carry on to do this thing. B and C got 13 and 14. So it's the next smallest. Now it's 45, 13, 12, 16, and 14. So the smallest one is 12. Yeah, this one you can ignore already. This one you can ignore already. Now it's only 14. Yeah, so you're trying to build among these 4 is 12 and 13. These 2 characters. You build another new subtree. So next one is 45, 25, 16, and 14. So should be 16 and 14. So which is D. You're trying to build another subtree. You repeat to do this. So the next one is 25 and 30. So you build another one. Last one, A, will be the highest frequency one. So you will construct this. This is called the radix tree. Is the bit string indicate the travel path from the root to the nodes. So A will be 0. Then B will be 101. 101. C will be 100. Then D will be 111. E will be 1101. F will be 1100. Yeah, so this is how they come out the code word. Once I come out the code word, I can start trying to use this code word to represent all the data I have. Then overall, you will find that the data, you can compress it. And as long as I have this code word, I can decode it easily. Just like a lookup table. And definitely that code word is unique. So this is some application to build a radix tree and to help you to solve some problem. Yeah, Huffman code is one of them. There are a few other applications to build this kind of tree. Okay. So this is just show you some example by using the binary tree. Although this is already more than 70 years, but today we even in especially people in working in communication, in the coding theory, even I saw people working in machine learning AI. Sometimes they have a huge data, but some data they use more frequently, some data you use less frequently. They still need to they will use this kind Huffman coding to compress their data. Or they trying to generate the unique code. Friday, I think I will just go maybe I think I probably will use the Zoom. I think I will use the Zoom to for the Q&A section. If you have any question you want to ask about the first half, maybe Friday I will make a consultation times for you to clarify your doubt. Yeah, maybe there's no YouTube video. I will use a Zoom. That would be better. Okay, so in the first part, in short, you have learned about the pointer, how to use the structure to define a node, then self-referential nodes. From that, you start able to construct a linked list. Then, then we will use the severals from singly linked list to circular linked list, doubly linked list, and then we also use the concept about the stack cube. Then that also is another kind of a special linked list. And then we'll learn about tree, which is a nonlinear data structure. You also use the self-referential nodes to construct the tree, binary tree. Here mainly we talk about binary tree. Then we use the binary tree to build a binary search tree. Binary search tree have some constraint. The left child must be all the number are smaller than the root, and the right child must be the number, the whatever is must be bigger, the value must be bigger than the current nodes, and every nodes must be fulfill this criteria, and then that's form a binary search tree. And then we also show you some problem to insert a nodes into a tree, remove a nodes of a tree. There's a tree balancing issue. And this one, Huffman code, is one of the example. Can be used a tree to solve some problem. I didn't go into too details. If you look at it carefully, there are something you need to find the smallest thing. So probably this one to find the to very efficiently to search the smallest one, the smallest frequency in the list. So why here I just simply set the list. Actually, it's not the list. You expect you need to use the another data structure called priority queue, and you need to do some sorting. Yeah, then you can really implement this coding tree efficiently. So this is probably will be in, you will learn it in the next level in 2000. Yeah, so I just introduce you this problem only. So I'm not going to show you how to implement them. Yeah, just let you know there's some example. Yeah. Okay. So that is today's lecture. Any other question? If not, that is today's lecture. Okay. Yeah, all this, I would say that again, the AVL tree, Huffman coding tree, all this, you mainly you need to understand the concept. This one is just introduce you a problem. Yeah, rather than said it's a concept, it's a problem. I didn't show you any, why is, this thing is efficient. I just show you that you can save the number of bit on average representation, you save 25% space. But yeah, then you just need to know the idea behind the concept. Then AVL3, like I said, you don't really have to know how to implement. Definitely I won't ask you during the test, ask you to implement the whole AVL3, that's for sure. Because just write that program, you already need to take more than 2 hours to do it. Not make sense. But I can ask you to do something similar to do the rotation, right rotation, left rotation, balance factor, that kind of things. Because those things can be done in half an hour. Of course, again, I won't ask you exactly do the left rotation or right rotation. You don't expect you simply memorize it, the particular rotation algorithm, you can solve the problem. You need to really understand how the rotation actually work, and how to really implement that kind of a structure change. How to modify the structure. The thing you need to realize is like right rotation or left rotation, you are trying to change the tree structure, and how to implement a function to change the tree structure is what you need to know. Not the right rotation or left rotation. It can be whatever kind of a structure change. You need to be able to do it. Yeah, I think that is what the expected learning outcome. Okay, anything else? If not, that is today's lecture. Thank you and goodbye.